Good morning, everyone. On behalf of Professor Shinji Tokonami sir, our esteemed foreign coordinator, and Dr. Rohit Mehra sir, Professor at Dr. B.R. Ambedkar National Institute of Technology, I extend a warm welcome to all the participants on the fourth day of the GIAN course. Further, without further delay, I now invite Professor Shinji Tokonami sir to commence the first lecture of today's session on radon and thoron. Tokonami sir, are you there?
Yes, can you hear me?
Okay, sir. You may continue your lecture.
Okay, thank you.
Okay.
Thank you for your kind introduction. So yesterday I explained the radon surveys in various countries, but today, at the beginning of this lecture, I will focus on Toron issues. Actually, this Toron issue is site-specific, especially in Asia. As you can see, Toron is often neglected in indoor environment because of its short half-life. Look at this. This is Toron Radon 220 with 56 seconds of the half-life. Due to its short half-life, Toron cannot travel far from its source. Its inhomogeneity of Toron concentrations in the environment. As you know, knowledge and research on Toron are limited compared to radon research. Not specifically covered in recommendations or regulations. In addition, no standardized measurement method is currently available. In the Toron study, we have to take into account polonium-216, lead-212, bismuth-212, and polonium-212 for those assessment. Toron can still be hazardous due to its progeny, including lead-212, the half-life of 10.64 hours, which can accumulate to significant levels in breathable air. Recent studies indicate that in some regions, the dose due to Toron and its progeny can be higher than that of radon and its progeny. Therefore, the global interest in Toron exposure is increasing. Toron interference can be regarded as one of the major uncertainties of radon measurement in indoor radon studies. Consequently, some studies are focused on developing discriminative systems to enable the distinct measurement of these isotopes. Here is our detector, Radioactivity, in cooperation with a Hungarian company. Here is an Indian detector, LR115 detector is used as a detecting material. Both of two detectors, they have same principle for discriminating two radon isotopes by using difference of half-life, their half-lives. In the Indian detector, there is a pinhole. Just only here is radon and toron gas. Radon and toron gas only can enter inside, and radon and toron gas are filled with this chamber. In the chamber, then the gas goes through the pinhole. Therefore, only radon gas can penetrate, can go through this pinhole due to long half-life of radon. Here, there are two methods, two ways for those assessment of toron and toron progeny. In direct method, this is the same as radon. Measure the toron concentration. According to Anscale report, they provided a typical equilibrium factor of 0.02, but I don't believe this is reliable. Then, anyway, after using the typical equilibrium factor, we can calculate equilibrium equivalent toron concentration. Multiplying exposure period, we get the time integrated equilibrium equivalent toron concentrations in becquerel hour per cubic meter. After that, using dose conversion factor, finally, we will get the effective dose. On the other hand, we can propose a direct method. As you might know, we can estimate toron progeny concentration directly. So we use the direct value of EETC, equilibrium equivalent toron concentration. Then finally, we get the effective dose. Dose assessment of toron with direct method, equilibrium equivalent toron concentration is expressed like this formula. D is the track density, tracks per square millimeter. C is a calculation factor, conversion factor. In our toron progeny monitor, only polonium-218 alpha particles can be detected with the thick energy absorber, because polonium-2 energy is the highest, higher than other radon progeny. Only this energy can be detected with CR39, solid-state nuclear track detector. Based on this principle, we get the conversion factor here, like this, and T is exposure period. This is a passive technique for toron progeny measurement. In our detector, the lowest detection limit of the equilibrium equivalent toron concentration is estimated to be 0.005 becquerel per cubic meter with a 90-day exposure. I will show you some result of toron surveys in Cameroon. The arithmetic mean of equilibrium equivalent total concentration was approximately 22 times higher than the world average value of 0.5 becquerel per cubic meter. This table summarizes a result of Toron survey, Toron and Toron progeny survey. 130 houses are covered in this survey. This figure shows the frequency distribution of Toron concentration indoors. Radon concentration in this survey is 103 becquerel per cubic meter as the arithmetic mean. Toron concentration was 173 becquerel per cubic meter. Equivalent radon concentration was estimated to be 41 becquerel per cubic meter. Equivalent Toron concentration was 10.7 becquerel per cubic meter. The contribution of Toron to inhalation dose due to radon and Toron exposure ranged between 12 to 67, 3 to 80, 7 to 70, and 7 to 60% in the north, south, east, and littoral regions respectively. From this survey, these findings emphasize the critical need to include Toron in the inhalation dose assessment for radon exposure. In Canada, simultaneous measurement of radon and Toron were conducted in a total of 3,534 residential homes across 34 metropolitan areas. Indoor radon and Toron concentrations are not correlated, and Toron concentrations cannot be predicted based on widely available radon data. Here is a result of the survey in Canada. On average, Toron contributes 4% of the radiation dose due to total indoor radon exposure. Regarding geographical locations of high background radiation areas, most of we have major high background areas in Asia. Yanjiang in Radon province, China. Takandiam, Mamuju in Indonesia. Karunagapalli in Kerala, India. In China, Yanjiang Guangdong province is famous for being one of the areas with the highest background radiation in the world. The Toron concentration was approximately 10 times as high as that of radon. Look at this. This is a summary of the survey. Radon concentration is 124 becquerel per cubic meter at the arithmetic mean. Toron concentration is 1,247 becquerel per cubic meter as the arithmetic mean. Equivalent Toron concentrations was 7.8 Becquerel-Barkik meter. Using these data, we calculated the annual effective dose. The annual effective doses due to radon and thoron progenies were estimated to be 3.1 plus minus 2.0 millisievert and 2.2 plus minus 2.5 millisievert respectively. The radon dose was comparable with the thoron dose in this area. Here's the frequency distribution of the total dose in China, in Yanjiang area. In Kerala, India, the geometric mean of inhalation dose was evaluated as 0.10, 0.44, and 0.54 millisievert for radon, thoron, and both of them respectively. This table shows the summary result of the survey conducted by our research group. High background radiation area and control area. Here's the number of house, the mean value, median value, and range. As you can see, the radon concentration indoors is comparable to that outdoor concentration. But in terms of thoron and progeny, a little bit higher than other countries. Therefore, the internal dose from thoron progeny was found to be more significant than that from radon. This figure shows the effective dose from radon and thoron exposures. Here's the number of doings. As our data analysis, there was no correlation between radon and thoron concentrations or between thoron and thoron progeny concentrations. Then we can say exposure to thoron cannot be predicted from radon exposure. Equilibrium equivalent thoron concentration estimation from thoron concentration involves significant uncertainty. Here's the relationship between thoron concentration and radon concentration. In this figure, the relationship between thoron concentration and thoron progeny concentration, namely equilibrium equivalent thoron concentration. Regarding Indonesia, Mammoth is recognized for having a radiation dose rate approximately 13 times higher than the normal level. In Takandian, the concentrations were consistent in both indoor and outdoor areas, including thoron in dose assessment is crucial. This table summarizes the result of the survey conducted by our research group. Radon, indoor, outdoor, thoron, indoor, outdoor, and equilibrium equivalent thoron concentrations, indoors and outdoors. The radon concentration ranged from, indoor radon concentration ranged from 42 to 900 becquerel per cubic meter. Surprisingly, outdoor radon concentration ranges also from 49 to 435 becquerel per cubic meter. So we calculated the annual effective dose based on the activity concentration of each radionuclide. Radon gave 3.4 to 12.1 millisievert. In the case of Toron, 5.1 to 17.7. As a total, annual effective dose was estimated to be 9.8 to 28.6. The arithmetic mean of annual effective dose, total annual effective dose, was estimated to be 18.2 millisievert per year. In Ireland, Europe, the first nationwide assessment in Europe of annual effective doses from both radon and toron. Between 2007 and 2009, long-term indoor concentration of radon gas and its airborne progeny were measured in 205 dwellings across Ireland. In 14 of these dwellings, the estimated annual dose from toron progeny was higher than that from radon. Here is a summary of the survey. Regarding toron concentration, arithmetic mean 22 becquerel per cubic meter, the maximum value 174 becquerel per cubic meter. Toron decay product concentration as equivalent toron concentration, arithmetic mean 0.47, the maximum value 3.8 becquerel per cubic meter. So we estimate annual effective doses from toron decay products, arithmetic mean 0.35 millisievert per year, a maximum 2.9 millisievert per year. In Japan, the first national survey was conducted using a Karlsruhe type radon monitor. Here is a sectional view of Karlsruhe type radon monitor. As I explained previously, the arithmetic mean radon concentration recorded was 20.8 becquerel per cubic meter. This monitor has had a relative toron sensitivity of 78% compared to radon sensitivity. Data are not suitable for estimating the national effective dose. So we revealed in this first survey, we revealed toron interference in the radon measurement with this monitor. Therefore, we conducted another survey. The second national survey was conducted using radon-toron discriminating monitors. The arithmetic mean radon concentration was 15.5 becquerel per cubic meter, approximately 5 becquerel per cubic meter, lower than that of first survey. Also, recently we conducted a small regional survey in Fukushima. Here's a frequency distribution of indoor radon concentration. The number of houses. The right figure shows the frequency of indoor radon concentration. Here's a summary of with a table. Radon mean radon concentration was 48 becquerel per cubic meter. The radon concentration ranged from 16 to 242 becquerel per cubic meter. In terms of toron, the mean value is 59 becquerel per cubic meter. It ranged from 34 to 97 becquerel per cubic meter. Also, we conducted radon toron surveys in Thailand, especially Chiang Mai province. As you might know, Chiang Mai is the highest lethal lung cancer mortality rate. Data were collected from 44 dwellings in between March and May 2020. Radon provided a greater annual effective dose to the residents than toron. Although Chiang Mai is the highest lung cancer incidence place, but radon concentration is not so high in this survey. The mean value of radon about 60 becquerel per cubic meter. The toron is lower than radon, 19 becquerel per cubic meter. But here is a equilibrium equivalent radon concentration and equilibrium equivalent toron concentration. Here's a summary of National Survey of Radon Isotopes. Radon exposure is subject to regulation. National Surveys provides essential data on the distribution of radon and toron concentrations across different regions and populations. Survey results highlight regional variations with some areas exhibiting higher radon and toron levels due to geological and environmental factors. Continued monitoring and research are essential for refining risk assessment and improving public health interventions. Collaboration between government agencies, researchers, and public health organizations is crucial for addressing radon and toron-related risk effectively. This is the end of this lecture 6. Dr. Mehra, I can receive some questions from audience.
Thank you very much, sir. So in case participants have any question, please unmute yourself and you may ask the question. So dear participants, if you have any question, then you may ask by unmuting yourself. So in case participants do not have any question, we can continue with your lecture, sir.
Yep. May I start again?
Yes, sir. You can start again, sir.
Okay. So I'm moving on the lecture 7, quality assurance and quality control for radon isotopes. Here are key messages from WHO handbook. Radon measurement in homes are easy to perform, but need to be based on standardized protocols to ensure accurate and consistent measurements. Long-term integrated radon measurements are preferred for assessing the annual average radon concentration within the house or other dwelling. High temporal variation of interval radon makes short-term measurements unreliable for most applications. The type of detector should be carefully selected since it influences the cost of measurement per dwelling and therefore the cost of a radon program on a national level. Quality assurance and quality control measures are strongly recommended to assure the reliability of radon measurements. Quality assurance means the set of planned and systematic actions put in place at specified stages of the radon measurement process to ensure confidence and accuracy of the measurement results. Quality control means the quality checks carried out within the radon measurement laboratory as part of the overall quality assurance system. Therefore, quality assurance and quality control measures are strongly recommended to assure the reliability of radon measurements. Quality assurance is a broad concept that includes all matters that individually or collectively influence the quality of measurement. Implementation of quality assurance standards and guidelines to ensure confidence in the measurement results is strongly recommended. All entities, such as individuals, businesses, government agencies, etc., providing measurement services, should establish and maintain quality assurance programs. Regarding quality assurance plan, at the heart of a quality assurance program is a quality assurance plan, which includes written standard operating procedures, written procedures for attaining quality assurance objectives, and a system for recording and monitoring the result of quality control measurements. Minimum detectable concentration. Any entity performing radon measurements should calculate and include the minimum detectable concentration for its measurement system in its quality assurance plan and report it with the radon measurement results. For calibration of detectors, individual for an active monitor or batch of passive detectors should be prepared. Detectors are exposed to the standard atmosphere under known conditions to get a calibration factor. That is a factor that converts the detector response to its true value. The detector is calibrated as received by the calibration laboratory. However, if any part of the detector that may influence the response to radon, that is a measured entity, such as a new batch of solid-state nuclear track detectors, foils, or a new readout microscope is used, the calibration should be updated. Use the detector under calibrated settings, high humidity, high attach fraction ratio to avoid measurement uncertainties. Calibration should be conducted annually or semi-annually, depending on the manufacturer's suggestion and licensing and certification agency requirements. So I'll show you the example of the calibration. Time variation of radon concentration in the radon chamber during the exposure test is observed using active radon monitors. Radon monitor was measured by AlphaGuard, which was calibrated by PTB, Germany. This figure exemplifies time variation of radon concentration. This is a photo of AlphaGuard. This is old type and new type. In our case, radon concentration, temperature, and relative humidity in the radon chamber vary over time during an exposure test. Radon concentration was measured using a pulse-type ionization chamber, namely AlphaGuard, calibrated by PTB as well. This figure shows the time variation of radon concentration, temperature, and relative humidity in the radon chamber. Here is a radon concentration and relative humidity, and this is a temperature. Using this facility, we can achieve the calibration for passive radon monitor. Here is the relationship between the time-integrated radon concentration and track density after exposure. Normally, in our case, we set 3 different exposure levels to obtain the linear relationship. Statement of certificate of calibration is then issued containing the following information. that is, the condition of the monitor are received, including any physical damage and settings of discriminator, voltage, background, and calibration factor as necessary. The measured background, the measured response to the reference atmosphere, the settings of discriminator, voltage, background, and calibration factor as calibrated, the date the calibration was performed, and the name and signature of the person responsible for the calibration. The level is labeled with a sticker saying that this device has been calibrated, the expiry date of the calibration, and the calibration factor. Background measurement. In terms of reactive monitors, over time, the atoms of lead-2 and 210 accumulate in the detector. And then the activity of alpha-emitting polonium-210 increases, and the background of the detector increases. Repeated measurement of detector background every half year or in shorter time periods if necessary. The measurement of the detector background should be recorded. Passive detectors, laboratory background measurements. The inherent background of laboratory equipment, which is used to analyze the detectors, must be measured and subtracted from the response of detectors used in the field. Background measurements are also used in establishing of detection limit and minimum detectable concentration. Field background measurement. Field blanks, detectors which are handled in the same manner as those for field measurement, but are not exposed to the ambient atmosphere or are stored in the low radon atmosphere. In terms of intercomparison exercises, as far as possible, entities performing radon measurements should participate periodically in inter-laboratory comparison exercises. Such exercises are typically carried out in one of two ways. First one, a continuous radon monitor may be chosen as a transfer standard and sent to several reference laboratories for exposure in systems for test atmospheres with radon, namely STAR. This was used in IEC standard. Once the continuous radon monitor has been received at the laboratory, the operator of each STAR compares the values generated by the transfer standard with the values generated by the system that is used to monitor the STAR. This method can only be used between facilities that have STAR. Radon measurement from STAR must be traceable to the primary national reference standard by an acceptable intercomparison method. Second, the other method requires a radon reference facility that has a STAR to host the exercise. entities that perform radon measurements then send devices to that facility for exposure in the star. The devices are returned, but the concentration of radon to which they were subjected is not disclosed. Each entity then reports its results to the host facility, which then issues a report comparing all the participant results with the conventionally true values. As a part of the intercomparison exercises, cross-checks for detector sensitivity to toron should be considered. Usually, the measurement is carried out at different radon levels, different relative humidity, and aerosol spectra, such as size distribution and unattached fraction. Dr. Mehra, may I have a short break?
Yes, sir, definitely, sir. So,
Yep.
so we are taking a break of now 15 minutes, and we will be, dear participants, we will be resuming the session at 11 a.m. after 15 minutes.